Yeah, so I originally timed this talk down to 25 minutes because that's what Steve said to do, but now we've got much more time than that. So instead of a highly caffeinated, fast-talking presentation, I'm going to slow things down a little. Hopefully you'll understand more that way. I guess it's fine if you really don't understand something, you can interrupt with a question. I may tell you to postpone it to the end, or maybe the answer may be a few slides in the future. But we can try interactive since we have a few extra minutes. I didn't know who was going to show up for PIRL. This is the first time it's being done. I give talks like this a lot, but usually I know my audience very well in advance. So hopefully some of what I say will make sense and possibly resonate with you. But again, we'll have plenty of time at the end to go into detail if anyone is interested. We're going to talk today about practicing the art of persistent memory programming on ordinary conventional hardware. So we're gathered here today mostly to celebrate the return of non-volatile memory after 40 or 50 years of absence. This is exciting for a number of reasons. To me, the most exciting thing about it is that it invites a dramatically simplified form of programming for the application developer. The application developer now has the option of leaving persistent application data in non-volatile memory rather than stashing it in some separate persistent store off to the side, like a relational database or a key value store, that has its own quirks and idiosyncrasies and rules. To my mind, the advantage of the style of programming that NVM invites is simplicity. We're getting rid of big, complex, opaque middleware layers. The application has only a single format for data, the in-memory format. There's no translation to some other format for persistence. Get rid of serializers, parsers. The programmer only has to think in a single paradigm. For example, the paradigm of imperative algorithms manipulating in-memory data structures. The programmer doesn't have to mentally context switch to some other way of thinking for persistence. For example, a declarative SQL manipulating data in relational database tables. Now, simplicity alone can often reduce the cost of developing software, make it easier to write correct code, and offer performance advantages beyond those obtained from fast new hardware. This talk is about persistent memory as a software abstraction. When I use the term persistent memory, I'm talking about not any new kind of hardware. I'll use the term non-volatile memory to refer to new hardware. I'm referring to a software abstraction when I use the word persistent memory and a corresponding programming style that can be implemented on conventional hardware without any NVM. In this talk, we're going to walk through some C and C++ examples for Unix-like operating systems. So, in some sense, the persistent memory style of programming occupies a fourth category of knowledge overlooked by the great philosopher Donald Rumsfeld. It's something we know, but we don't know that we know it. The elements of persistent memory programming are a handful of idioms and tricks that are individually well known. But the composition of these techniques into what I call the persistent memory style of programming doesn't get the attention that it deserves. I don't see it in textbooks for undergraduates. I don't see it in documentation for developers. What are the elements of persistent memory programming for conventional hardware? Well, we start by resolving to lay out application data in file-backed memory mappings. We typically use sparse files for the backing files because that offers a pay-as-you-go storage footprint model. The backing file that will eventually be occupied by persistent application data begins life as logically an enormous file filled with zeros. It has zero storage footprint, and as the application fills it up, then you actually start consuming resources. We use good old-fashioned pointer casts to interpret the contents of file-backed memory mappings as application-defined data types. Almost always, we're going to layer on top of raw persistent memory a persistent heap abstraction that allocates persistent memory from a file-backed mapping, and we're going to see how easy it can be to slide a persistent heap beneath complex legacy software that was never intended to be persistent. For those of you who need a refresher, mmap is just a standard system call that establishes a correspondence between byte offsets in a file and addresses in memory, allowing the developer in concept to manipulate the backing file in the file system with loads and stores to its in-memory image. So as a warm-up exercise to remember how all this works, we're going to write a simple program to substitute lowercase abc with uppercase abc by doing an in-place substitution on a memory mapped file. Okay, so we call mmap, to map a backing file containing our data into the address space of our process, we use a pointer cast to say we're going to just trivially interpret the contents of this file as a byte array. Once we've done that, we can walk through the contents of the file as though it were memory, because now it is. We're accessing persistent memory by loads, identifying lowercase abc at consecutive memory locations, replacing them with uppercase abc at consecutive memory locations. Now, there's a much easier way, of course, to perform the same transformation here, and that's with a one-liner on the command line, sed. It's instructive to contemplate why this program is usually substantially faster than the sed alternative. Both this program and sed must read every byte of their input. There's no getting around that. But sed writes as many bytes as it reads. By contrast, this program only pushes down to durability the pages of the in-memory image that it has modified, which could be far less data. Okay? Now, typically, a program doesn't want to interpret persistent data as an array of bytes. It wants to use rich application-defined data types. And this example shows in simplified form how you can do that. We have an application-defined data type, just an ordinary C struct. This time, we're going to interpret the contents of our backing file as an instance of that structure. Once we've done that, again, we can use loads and stores to manipulate persistent data in the backing file. This time, we get the same degree of type checking that we're accustomed to in an ordinary C program. Now, this first pointer cast must be done with extreme care. If we botch that, the result is mayhem. But once you get that right, all the rest of the type checking just works. In the next example, this slide and the next slide, we're going to talk about how easy it can be, in the simplest case, to define a persistent heap and then slide it under something complex. Okay, there's not going to be a quiz on this. You don't have to you ruin your eyesight by looking at the actual all the details, but I'm just trying to convey the order of magnitude of complexity required in this task. It can be very simple. Later in the talk, I'm going to announce the release of a library that includes some example code. This is one of the examples from it, example number 2. Right? The entire example program is on the order of 100 lines of code. Here in simplified form, in edited form, is what it does. So we have our persistent heap begins with a header that will occupy the first 4 machine words of our backing file. The header contains, in the first word, an address at which we resolve to map the backing file every time we use it. Then there's some allocator bookkeeping information and a root pointer. The root pointer in a persistent heap is the responsibility of the application to ensure that all live data in the heap is reachable via the root pointer. Okay? We have replacements for malloc and free. Function M is a replacement for malloc. Function F is a replacement for free. It's just a bump pointer allocator. The free doesn't attempt to recycle memory, it just leaks it. Yeah.
How can you be certain that you're going to map it the same way?
That's coming in a few slides. The short answer is there's no portable way to do it, but there are heuristics that always work in practice. So this is a fundamental decision and a controversy among people who work in this space. Right? All right, so once we've defined a completely low-budget, bare-bones malloc free pair, and then this is a C++ program, we overload global operators new and delete to use our allocator. Right? So every time C++ needs dynamically allocated memory, it's going to allocate off our persistent heap. Okay, now this is the second part of the program. We're going to attempt to read the first word of our backing file to see whether it has already been initialized, in which case the first word of it is going to contain the address at which we must map the backing file this time around. If we find an address in the backing file, we map the backing file there. Otherwise, we use a heuristic that I'm not showing here to find a quiet neighborhood in the address space where we can reliably map our backing file this time and next time and forever after. We map the backing file and set our persistent heap to point to the return value of mmap. Now we've got an entry point into a C++ STL map that will become a persistent map. We have to do some initialization first. If the backing file is a newborn persistent heap, that is to say it's just a bunch of zeros, well, we have to initialize that 4-word header I showed you on the previous slide. We have to memorialize the address at which we're mapping the heap now, because that's where we're going to map it in the future. We set up some allocator bookkeeping information. We allocate a persistent map by just calling new map. Remember, we overloaded new and delete, so this allocation is going to happen off the persistent heap. Then we set the root pointer of the persistent heap to the entry point to the map. Okay? If we're dealing with a backing file containing an already initialized persistent heap, we don't do as much work. We just find the entry point to the persistent map by following the root pointer. Right? Now, after these few dozen lines of preliminaries, we can use the map as we would an ordinary ephemeral map, but it is persistent. How do we know it's persistent? Well, here in simplified form is how you run the program on the previous 2 slides. We're going to create, using a command line utility, a sparse backing file. For convenience, it's often nice to have it a multiple of the system page size, which is 4K on my system. We're going to invoke our example program, directing its attention to the backing file, and we're going to spit some words into it. Right? What the program does is it counts the frequencies with which it has seen every input word. We tell it to dump the contents of its map, and sure enough, it's seen bar once and foo once. No surprises there. Now the program exits. We start it again, directing its attention to the now initialized backing file containing our persistent heap. We spit a new word into it, we spit an old word into it, ask it to dump its contents, and sure enough, it remembers the words that it saw on its first invocation. So this is a poor man's persistent balanced binary tree. It can be less than 100 lines of code. So this is a topic that came up earlier from an audience question. A fundamental decision that you must make when practicing the persistent memory style of programming is whether your persistent data is going to be relocatable or whether you will require it to be mapped at the same virtual address every time you use it. There are trade-offs involved, and I've tried to summarize those trade-offs here. If you, as in the previous example, resolve to map your persistent data at the same virtual address every time you use it, well, that allows you to use ordinary C-like pointers, right, which are familiar and convenient. That, in turn, makes it possible to easily retrofit persistence onto legacy libraries or entire programs, as we saw with the C++ STL map. The downside is that there is no standard portable way to find a region of your address space where you can reliably mmap anything next time. There's no guarantee from POSIX or from Linux or anybody else that the address range that worked for you last week won't be occupied by libc.so next week. Right? In practice, there are heuristics that happen to always work, but we don't get any guarantees here. More importantly, if you're mapping persistent data at the same address every time, that inhibits sharing between independently developed applications. If I have persistent data that must be mapped at address 47, and by chance so do you, we can't map your persistent data and mine into the same process at the same time. Okay? So my advice for the students I lecture to is that you should consider using fixed mappings for persistent data that is private to a process in the same sense that a conventional heap is private to a process, and for situations where you want compatibility with existing code, as we saw with the C++ STL example. Now, if on the other hand, you decide at the outset that your persistent data are going to be, your data structures are going to be relocatable, well, that makes it easy to share persistent data among independently developed applications, and you're not relying on heuristics and tricks that aren't guaranteed to work to find a part of your address space where you can repeatedly map data. It's more standard and more portable. The downside is that you can't use conventional pointers. You have to use something like offsets instead, offsets relative to the base address at which persistent data are mapped. That's less convenient and less natural than pointers. And more importantly, it's inconvenient with existing pointer-based code, of which there is a lot in the world. Okay? So my advice is to consider relocatable data structures. You may have to use them. If your persistent data is not private to a process, it's more like a database to be shared among different processes and different applications. Okay? So there are a couple of rules you have to follow when programming in the persistent memory style. Many of them due to the need to avoid bugs stemming from mismatches in the lifetime of different kinds of memory. it's almost always a bug, and this is easy to see, it's almost always a bug if you have a pointer or other reference from persistent memory to non-persistent memory. Unless you really know what you're doing it deliberately, that's usually a bug. You have to keep in mind that things like static, external, and global variables are reset to 0 every time your program restarts, right? Whereas persistent data by definition is not. If you're using C++, you have to watch out because sometimes C++ stashes function pointers in your objects invisibly. Those function pointers point to someplace sensible the first time you run your program, second time maybe not so much. Old rules remain unchanged. So in multi-threaded programs, data races are always illegal. So if in one thread you're calling MSync to push changes in the in-memory image of persistent data down to the backing file, there had better not be any other thread that's modifying that in-memory image during the MSync call. Otherwise, you've got a data race, which remains illegal. Furthermore, if you're embedding things like synchronization primitives, mutexes, for example, in persistent... Hello? Hello? Did we run out of battery? Is this working? Okay, so I'm gonna lean over. Okay. If you're embedding mutexes in persistent data structures, you have to realize that that when your program restarts, you may want them to be reinitialized. For instance, unlocking locks. If you want inspiration for one way to do that, take a look at Intel's Persistent Memory Development Kit, PMDK. It has a sophisticated and carefully thought out way of helping programs to reinitialize things like synchronization primitives upon restart. There are other ways to do it, but this is one way, and it's well thought out. So far we haven't talked about what happens when something goes wrong. So if your application must tolerate unforeseen crashes due to, for example, power outages or OS kernel panics, application process crashes. So far, we've got a problem if we're using conventional mmap and MSync because failures during an update can corrupt the backing file containing persistent data. The basic problem is that conventional mmap and MSync don't allow the application to update the backing file atomically in the presence of failure. More generally, in POSIX and Linux, and with the default file systems in Linux at least, there's no standard portable way for an application to atomically update application data in a file in the presence of failures. Now, yes, it's true, file systems go to great lengths to protect the integrity of their metadata from failures, but they offer no similar protection for application data. It's kind of like a police department whose only goal is to prevent cops from being mugged. That's a fine goal, but it shouldn't be the only goal. As it is, constructing atomicity mechanisms from the ordering primitives that you're given, things like fsync and msync, is left as an exercise for the developer. I think this is an appalling situation. And if developers weren't such wusses, they would riot. Which brings us to the subject of my research for several years when I was at HP and the subject of my ongoing interest now, failure atomic msync. It is what the name says it is. It is a semantic strengthening of conventional MSync, but it gives you a strong guarantee that the backing file will always reflect the most recent successful MSync, even if failures occur at any time. All we're doing is restricting the possible behaviors of conventional mmap and MSync. We're not introducing any new behaviors, so it's easy to reason about. This is a subset of something you already know. Now, failure atomic MSync can be implemented efficiently in the same sense that mmap and MSync are efficient. Ordinary MSync and failure atomic MSync only push down to durability those pages of the in-memory image of a mapped file that have changed. What is failure atomic MSync good for? Well, tolerating fail-stop failures, things like power failures, kernel panics, application process crashes. Bugs or defects that directly corrupt the backing file are not tolerated. So for example, if you have a buggy storage device, it's not going to help you. If you have corrupted the in-memory image of your persistent data and then you call failure atomic MSync, well then you're hosed, right? It's not magic. It doesn't protect you from yourself. It doesn't fix your C bugs. So when you're using failure atomic MSync to practice the persistent memory style of programming on conventional hardware, you have to follow all the same rules you had to follow for mmap and MSync and a few new rules. You should only call failure atomic MSync when your data, your in-memory image, is consistent. That is to say, whatever application level invariants must hold. You only call FAMs when they do hold. And right before you call failure atomic MSync, that's a great time to check those invariants, right? Because before you commit corruption to the backing file, if you detect corruption, just assert 0. If you write your program in the correct way using failure atomic MSync, crashes are always safe, right? You can crash with confidence. That's one of the hardest things for experienced developers to learn when programming in this style. So there have been several implementations of failure atomic MSync in the past. I've worked on 3 of them when I was at HP. The first was a user space library that I released around 2012. The failure atomic MSync aspect of that library was deeply entangled with other things, and it wasn't cleanly separable. Several colleagues and I also worked on a Linux kernel prototype of failure atomic MSync, which inspired our friends in the HP storage division to implement a generalization of failure atomic MSync in the HP advanced file system, which is a Linux file system that ships in appliance-like storage products. Right here at San Diego, Professor Swanson and one of his students implemented failure atomic MSync in the Nova file system a few years ago. Currently, there are at least 2 other implementations of failure atomic MSync that I'm aware of. Christoph Helvig, who we heard about in the keynote this morning, has implemented it in XFS. He believes the implementation to be complete, but it has not been tested to his satisfaction yet. So it's not generally available. The other more recent implementation is a library that I've written called FAMOUS, Failure Atomic MSync in User Space, that I'm releasing today. I'm going to give you the URL in a few minutes. So we've had a lot of experience using failure atomic MSync to retrofit crash resilience onto existing software. The first 2 examples involve the Kyoto Tycoon networked key value store and the SQLite embedded database. Both of these have modes of operation that are not crash resilient, right? They're intended to be fast but not safe. It so happens that both of these products lay out their data in memory mapped files, so it was easy to transform their unsafe, non-crash resilient modes of operation into crash resilient modes of operation by replacing conventional mmap MSync with failure atomic MSync. That took 1 or 2 lines of code change in each case. A team of academics led by a member of the JavaScript Language Standards Committee prototyped a crash-resilient JavaScript interpreter based on Google's V8. They took my user space persistent heap based on a user space implementation of failure atomic MSync, slid it underneath V8. That took one developer with lots of support and encouragement, some number of weeks, probably more than 2 months to do. Finally, HP has a line of digital printing presses called Indigo. It's a $1 billion business. Each one of these presses can cost $1 million. It fills a room, and they had a problem. Power outages are surprisingly common in the environments in which these presses operate. And a power failure would take down the press, and because it corrupted data structures, it would take hours or days for the press to get back into full production. It's a $1 million piece of capital equipment. It's down for hours or days because of a 2-minute power outage. Right? This isn't good. The customer doesn't like this. Sometimes Indigo would have to send a field engineer to the customer site to stand the press back up. Indigo had tried at least once to rewrite their print workflow control software to make it crash resilient, but they couldn't do that. It was too hard of a job. It was complex legacy code that was highly performance tuned. I gave them a user space implementation of failure atomic MSync. One developer working for a couple of weeks was able to slide that underneath their print workflow control software. That reduced recovery times following crashes from hours or days to about 6 minutes. So the takeaway from experiences like this is that failure atomic MSync can make it very easy to retrofit crash resilience onto software that was never intended to tolerate crashes. So what are some things that I like about failure atomic MSync? Well, you can implement it in a whole bunch of different places. We've implemented it once or twice each in the OS, in the file system, in a library. There may be other modes of implementation that are possible. I know an academic who's working on one, but that hasn't been published yet. In most implementations of failure atomic MSync, the storage technology that provides durability is just a placeholder. You can use individual storage devices, locally networked RAID arrays.
I need better batteries.
Okay. Again, the storage layer that provides durability is a placeholder. You can use individual storage devices, your favorite RAID array. You can use geographically replicated cloud storage, anything you want. This allows the users and the operators of applications to trade off monetary cost against other considerations like durability, availability, performance, endurance, without changing the application at all. Some implementations of failure atomic MSync, in particular user space library implementations, are friendly to large data sets because, well, persistent data lives in a file, and how big can a file be? Well, that depends on how much storage you can afford. The amount of data that can be in flux at any given time is limited by the virtual memory size of the process that is manipulating it. The so-called transaction size, the delta between consecutive MSync calls, the amount of data that changes, is limited only by free storage. Now, the programmer gets an ergonomic benefit too. The programmer writes code that doesn't have begin transaction, end transaction calls, and that's good because history has shown that pairing malloc with free, lock with unlock, open with close is a source of bugs. In failure atomic MSync, everything between consecutive MSync calls is an atomic durable transaction. All right, so we've seen that it's easy to make failure atomic MSync makes it easy to retrofit crash resilience onto legacy software. Because it's just a restriction on the possible behaviors of conventional MSync, it's easy to reason about. There's one place where you should check your global invariance in your code, and that's right before you call failure atomic MSync. Some implementations give you versioning of your data for free. Right? The implementation, the library implementation that I'm introducing today has that property. And again, you can implement failure atomic MSync on conventional hardware, ordinary DRAM, spinning disks, or your favorite block storage technology. So Famous is a failure atomic MSync in user space. It is the library that I'm releasing today. It's very simple. There are two basic things that every implementation of failure atomic MSync must do. It has to track which pages of memory have been modified since the last time you called MSync, and Famous does that using a Linux feature called soft dirty bits. We also have to update the contents of the backing file atomically with respect to failure. Famous just uses simple undo logs. If you keep your undo logs around, you get data versioning for free. Right? You can use your undo logs to revert to a previous version of your data whenever you want, where every call to failure atomic MSync defines a version. I'm giving you the URL here containing the preliminary release. I warn you that it has not yet been tested to my satisfaction. I have not subjected it to sudden whole system power interruptions, which is something that I did with all of the 3 other implementations of failure atomic MSync that I worked on in the past. You have been warned, you're adults, you decide whether to use it for anything important. In this first release, I know that performance is far from optimal. There are too many fsync calls. That's fairly obvious if you read the code. But I thought it was important to expose this at PIRL, so there it is. If you have any questions, feel free to write to me. I'll do my best to answer them. So to wrap up, what I've described today is persistent memory in the sense of a software abstraction and a corresponding style of programming that offers some of the same attractions and benefits as the style of programming that non-volatile memory invites. But persistent memory, as I've described it, is implementable on conventional hardware. If you're worried about failures corrupting your persistent data, failure atomic MSync is a mechanism to address that concern. Famous is a new library implementation of failure atomic MSync for Linux systems. The URL is there. And now I think we have plenty of time for questions.
What's the license?
It's an open source license. It's AGPL.
Okay, so I can use it in my code.
Yes. I mean, you read the license, but
So I have a comment about C++, because you showed that a normal C++ program, even with STL, can be adopted with persistent memory using this technology. But one of the problems I found by developing here is that standard committees don't like what we are saying.
Oh, of course. So I think Andy Rudolph told me at NVMW, he told us at NVMW that there might be, in C++ 17, mmap might be illegal or something like that. Right. So, yes, and C++, molts every 3 years. And who knows what it will be, what it will be like in 3 years. Yes, I understand. I'm sorry, I interrupted you. Please.
So yes, we are trying to work with standard committees actually on making sure that at least mmap is legal so that you can have objects that span more than a life cycle of an application. But it's been an uphill battle, honestly.
Yeah.
I was just commenting that I think you should put that in your slides in the future because it's very important for people to know that some people might object to this kind of software, right?
It's easy to provoke the anger of C++ purists. An earlier version of this deck did contain mention of what the thing that Andy passed along at NVMW, but then I had to trim it down to 25 minutes to fit the slot. So I guess my thought is, my understanding is that there is a proposal in the C++ community called Bless, right? Which is a way for the programmer to say, no, trust me, I know what I'm doing, and please allow this mmap to proceed. And if that's approved, then the problem goes away. A more profound problem with the example program that I showed you, one that you have probably encountered, is that in C++, there are constructors that are called before main executes, and they can be called in an uncontrollable order. Now think about that. You, the programmer, write a single-threaded program, and blocks of your code are invoked in an order that you cannot control. Is that why they call it a programming language? So if any of those constructors allocate dynamic memory, well, it ain't going to be persistent memory because the persistent memory allocator hasn't been set up, right? So that's another problem. I know a man who's on the C++ language standards committee who says, you should not write code with that kind of constructor that gets called before main because it is a fertile source of bugs. At least one member of the committee believes that it is a defeature.
Well, I know you said that performance is not optimal. Do you have anything when it is optimal, what we're talking about with respect to not worrying about?
So I'm going to answer. I'm not going to answer the question in the context of this library, on which I have not conducted extensive performance experiments. Right? I haven't done the power fail test to convince me that it's correct. I don't care how fast it is if it's wrong. Right? An implementation of failure atomic MSync is possible. Where the performance cost is easy to estimate. For every page you've dirtied since the last time you called MSync, well, you have to write that, right? And you have to do the moral equivalent of an fsync, right, on that data, right? So if your durable storage device is one of these fancy newfangled non-volatile memory devices configured to expose a storage interface, then that write is just a mem copy. Right? And there might be some cache flushes involved with the fsync. So it can be that fast. But if you have non-volatile memory, my advice to you is check out things like PMDK, because that's almost surely going to be faster. Right? What I'm talking about here is a way of practicing the persistent memory style of programming if you're working with conventional hardware. That is ordinary DRAM and block address storage.
I just wanted to add to the cautions that you said as far as mapping in something that had been previously put like persistent memory, and that is that it's also very fragile as far as compiler revs, that we found that alignment and packing and all can be different, and so your data structures are corrupted when you try to access.
Yep.
Kind of on a similar follow-up, if you try to run a newer version of your program with persistent data structures, do you have any problems with how to reordering things?
Well, the C language standard mandates that if you lay out variables in a struct, they're going to appear in the order in which you've laid them out. Compilers could, one version of a compiler to the next might pad things differently. So that's an issue. It's never bitten me, but it could, right? So the developer would be wise to very carefully pack data structures manually. And a bigger problem is, what if requirements on your application change and the boss tells you, oh, you have to add a new field to that struct, right? All of your data structures, in the style of code that I've shown you, all your data structures are densely packed on the heap, right? So it's not easy to add a new field to a struct. You can postpone problems by padding structs with empty space in anticipation of future needs, but in the worst case, you have to write manual reformatted code. I don't know a way around that. Yep.
So if I understand your example correctly, program will restart with the main function and it will recover all the data structures that it knows from the heap, right?
That is correct.
So what happens in a multi-threaded program where threads might have allocated memory that has been taken but not really linked anywhere?
It is, so is your concern that a crash will cause a leak? Okay, so if you write your program incautiously, that can certainly be the case. If you write your program carefully, it will not happen, right? So if you're using failure atomic MSync, right, you have to be careful to call MSync only when your data is consistent, which means that all live data is reachable from the root pointer. Right? That's just a rule. If you've broken that rule, then yes, a crash can cause a leak.
So that's where my multi-threading aspect comes in. So if I have a multi-threaded application, for instance, a database function SQLite, then I need to introduce a point where all threads synchronize and decide that this is an atomic point that I call.
Well, so as with conventional MSync. Hello?
I think you're hitting the bottom.
Oh, I'm hitting the bottom. Am I doing this?
Maybe.
Oh,
No?
sorry. Sorry if it was my fault. Yeah, I forgot what I was saying. If you're using conventional MSync or failure atomic MSync, you have to make sure that no thread is modifying the in-memory image of your persistent data during an MSync call. That's just a rule. Otherwise, you have a data race, right? So does that help you? Does obeying that rule, which you have to obey, does that go any distance toward alleviating your concern?
Okay, so you're saying you're not introducing any more requirements than there were before?
In terms of requirements on avoiding races in multi-threaded code, no. Yep, go ahead.
Something to that question. So this tool, this library, can only be used to modify existing applications with very small changes for applications that already use MMAP for some storage. If you have application that uses a heap, so in dynamic allocates memory, then you have to kind of reorganize the data structure so that everything is reachable from the root.
Actually, well, right. So obeying the requirement that all your data is reachable from the root, that requires you to do some work, right? But it turns out that that's not as annoying as it sounds, right? It would take longer than the time we've got, but if you're concerned with the difficulty and the fuss of following that rule, basically making sure the application can find its persistent data from the root, that's actually less of a big deal than you would think. And I can explain why, but it would take a couple of minutes, so we can talk offline. Are we done? Thanks, guys.